Hello, good morning, class. Can you hear me? Okay. I can see your responses. All right, I can see your responses. The link, in case if you get logged out, maybe due to network instability or any challenge whatsoever you may face, you can go back to the LMS page and follow this class live. The link to the YouTube has been placed on the LMS. So you can follow this class live on the LMS page. Okay. Some of you are still entering, so I'm giving you very few minutes, like 1 minute to enter the class. All right. All right. I'll be sharing the screen with you in a moment. All right, class. In the last class we briefly looked at some definitions of acids and bases, where we considered Arrhenius definition, Brunelleschi definition, which talks about acid is a proton donor and a base is a proton acceptor. We also looked at Lewis' definition of an acid. And Lewis basically defined an acid as electron pair acceptor and a base as electron pair donor. We also looked at some examples of Arrhenius acids, Brunelleschi acids, and Lewis acids and bases also. And I gave you a class quiz, a question which we solved together. And after then, we looked at the strengths of acid and bases. And we say we can define the strength of an acid and basis in terms of the degree of dissociation, that is the alpha, which can be between 0 and 1, or maybe in form of percentage, that would be 0 to 100%. A strong acid dissociates completely in solution. A weak acid dissociates partially in solution. We also looked at the concept of dissociation constant, and there we looked at the ionization of water, and we also treated the dissociation constant of water at equilibrium. We said that the reverse process is highly favored, is better favored than the forward process. From there, we also described the hydrogen ion concentration of water and the hydroxide ion concentration of water to be the same at equilibrium at 25 degrees C, and that is 1.00 times 10 raised to the power minus 7. That can change with temperature. If you vary the temperature, that value will very much likely change. After that, we also considered the dissociation of an acid, and there we wrote an expression for the dissociation of an acid, that is K subscript A, and that is the concentration of the hydrogen ion multiplied by the concentration of the anion divided by concentration of the aqueous acid. And we introduced a concept which is the activity. Instead of mentioning concentration, molar concentration, we introduced the parameter which is activity. So we can be talking of the activity of the hydrogen ion, the activity of the anion. We say this one is negative, not positive, and the activity of the acid on its own. And if it's a weak acid, then the activity is not the same as the concentration. That is, the activity is not equal to the molar concentration for a weak acid. And the reason is just that the degrees of dissociation is not equal to 1. So that acid, a weak acid, does not dissociate fully in solution. After that, we also consider the dissociation of a base, and there we wrote an expression which is K subscript B, which represents the dissociation constant of a base to be equal to the concentration of the HA, the OH minus, divided by the concentration of that anion, of the anion in solution. And we said that if we multiply equation 5, what is equation 5? That is this expression, which is, this expression, which is concentration of H plus, concentration of A minus, divided by HA. So let us take that to the other side. We have concentration of H plus, A minus, divided by the concentration of HA. If you multiply this equation 5 by equation 6, what you will observe what you will observe is that, okay, let's look at it together. We have A raised to power minus 1, that's the anion, A minus A. We have the A minus A, the concentration of it for the equation 5. And for the equation 6, we also have that A minus, but it's in the denominator. So this numerator cancels this denominator, and that goes away. Then look at this parameter, which is the concentration of the weak acid, or maybe you're referring to the weak base, that's HA. Just look at the solution. You have the same parameter also at equation 6. That's concentration of HA. So that parameter in the denominator cancel the same parameter in the numerator. So we have the anion going out of the expression and also the HA going out of the expression. We're only left with the concentration of the hydrogen ion and the concentration of the hydroxide ion, and our Kw, which is the multiplication of the acid dissociation constant with that of the base dissociation constant by multiplying equation 5 and 6, will give us H plus, that's the concentration of the hydrogen ion multiplied by the concentration of the hydroxide ion. So this is the expression that we have. Also, if you want to determine the parameter that we call pKa, that's another way of writing the dissociation constant of an acid. But now we are considering the power to which it is raised, and that is on the logarithmic scale. So we can write this pKa to be equal to minus log to base 10 of the acid dissociation constant. And if we're referring to the base, we'll also write the pKb to be equal to minus log to base 10 of Kb, minus log to base 10 of Kb. Ka values and Kb values for acids and bases respectively can be small values. And in order to get them in form of number, in form of integers that you can easily, or maybe natural number that can easily make reference to, we express them in form of pKa. Then looking at this, our Ka, pKa and pKb, as they relate to the log of the Kb, you will see a negative sign in between them, which suggests to us that if pKa is increasing, it means our Kb is actually small. And if we have large Kb, then we have small pKb. So that is all we mean by this expression under this note that I wrote for you. So if you have large Ka, that implies small pKa, and that suggests that we have a strong acid. It means that acid will dissociate very well. If we have large Kb, that can be related to small pKb, which suggests that we are dealing with a strong base. So very briefly, let us move on to another. Okay, this is table 1. Possibly you may be able to see some parameters there. And the first set of parameters relates to the Ka, that is the acid dissociation constant of this set of acids that we have listed here. So we have the dissociation constant written here. That is adapted from this textbook, Fundamental Physical Chemistry by these authors, and that is the revised edition. So if you have this textbook, you can look more and check more of these values. They have been experimentally determined for Ka and for Kb. So you can go through that at your own convenience. So briefly, let us go to unit 5 of this section, which is acid, bases, and pH. And this unit 5 will be considering the acid-base equilibrium in aqueous solution. And other that we'll be determining the pH concept. So we'll be relating it to the pH of a strong acid, the pH of a weak acid, the pH of a strong base, and the pH of a weak base. And what are we expected to achieve at the end of this unit 5? We should be able to define the pH of a solution. And that is one of those things we'll be able to acquire, to gain at the end of this unit. What is pH of a solution? Possibly some years ago, you were introduced to this concept in secondary school, maybe SS1, SS2, SS3. So how can you define pH? Is the pH of a strong acid the same thing as the pH of a weak acid? How can you calculate the pH of an aqueous solution of a strong acid? And how can you calculate the pH of an aqueous solution of a weak base? We'll be looking at that under this unit. And also we'll be calculating the pH of an aqueous solution of a strong base and the pH of an aqueous solution of a weak base. So what is pH precisely? That is a way of expressing the acidity or alkalinity or maybe basicity of a solution. When you are provided with a solution, maybe solution A, then solution B, and you look at it, maybe you have, it may look colorless, no matter how it looks. How will you be able to say that this is an acid? Is A an acid or is B an acid? Don't just say because I wrote A there, maybe A is acid, B is base or something. It may be acid, maybe base. So how are you going to describe that? And also, if you know that maybe A is an acid or maybe B is an acid, which one has better acidity? Which one is more acidic? Which one is more concentrated? So we can be defining this pH in form of the concentration of the hydrogen ion. And the pH in terms of that is the negative logarithm to base 10 of the hydrogen ion concentration. We are using hydrogen ion concentration, assuming that the solution, the acid dissociates properly in solution. If it doesn't, we can be using another term, which is the activity of the hydrogen ions. The activity of the hydrogen ions. So we'll be relating the pH of that solution to negative logarithm to base 10 of the activity of the hydrogen ion, instead of calling it the concentration of the hydrogen ion, depending on the degree of dissociation of that acid. So what does this P represent? This small letter P, see the way I've written it. I wrote it as small letter P and capital letter H. This small letter P means potence. That is a German word which means the power to which 10 is raised. The power to which 10 is raised. And that is how we can describe, that's one of the ways in which you can describe the acidity of a solution. So this pH is equal to minus log to base 10. Let's just call it the hydrogen ion concentration. So, okay. This pH concept also has its own scale. If we have, maybe we'll talk about it later. If we have the pH ranges basically between 0 and 14. You can have something beyond that, but on a normal pH scale, we talk about 0 to 14. If you have a pH of 0 to something less than 7, then we'll say that that solution is acidic. That is, if the pH is less than 7, the solution is acidic, and the hydrogen ion concentration is greater than the hydroxide ion concentration. If the pH is greater than 7, then that solution is basic, or it's an alkaline solution, and the hydrogen ion concentration is less than the hydroxide ion concentration. But for a neutral solution, the pH is 7, and the hydrogen ion concentration is equal to the hydroxide ion concentration. And that is a very good way in which we can differentiate between an acid and a base. So here we'll be looking at, under this section, we'll be looking at the pH of an aqueous solution of a strong acid. After that, we'll look at the pH of an aqueous solution of a weak acid. They will also consider the strong base and a weak base. But here under this section, we'll be looking at the pH of an aqueous solution of a strong acid. By strong acid, we mean that the acid fully dissociates, it completely dissociates in solution. And that suggests to us that the activity of the hydrogen ion is approximately equal to the hydrogen ion concentration. Okay, so the pH of a strong acid solution follows this expression, which is equation 10. pH equals to minus to base 10 minus log to base 10 of hydrogen ion concentration. How can we apply this formula? HNO3 is, HNO3 is a monobasic strong acid. It has one ionizable hydrogen ion. So when it goes into solution, it releases just 1 mole of hydrogen ion. So consider this example. Determine the pH of 0.20 molar. We have already said that molar means mole per dm cubed. 0.20 molar HNO3 solution. How do you solve this? First thing is you have to know how many number of moles of the hydrogen ion does it release in solution. So don't just look at the concentration. This concentration is just the concentration of the entire acid solution. If the acid does not release all the hydrogen ions in solution, then this concentration is not the same as the concentration of the hydrogen ions. Also, if the acid has more than 1 hydrogen ion in solution, then this concentration may not also be the same as the concentration of the hydrogen ion in solution. We'll consider 2 examples very briefly. So look at this equation. HNO3 gives us 1 mole of hydrogen ion and 1 mole of NO3 ion, that is the anion. From this expression, what is the number of mole of the HNO3? 1. You can see that from this expression. So 1 mole of HNO3 releases 1 mole of hydrogen ion concentration and also 1 mole of NO3 ion. I hope you are following this. Let me get your response before I go further than this. Are you following what we're trying to do? Hello, are you following what we're trying to do? Okay, I can see your responses. All right. Okay. If you are not following what we are doing, you can put your question under the chat section. We'll go through it and provide answers to it, possibly in the next class. All right. I can see your responses. So let's go back to that example. So we have 1 mole of HNO3 giving us 1 mole of hydrogen ion and 1 mole of NO3 minus. Note the way I'm calling it. I'm calling it ion, not ions. So we call it ions, not ions. All right, so we move on. So if 1 mole of HNO3 gives 1 mole of hydrogen ions, that suggests to us that 0.20 mole in 1 dm cube of solution, that's 1 liter solution, will also release 0.20 mole of hydrogen ions in 1 liter of solution. 1 dm cube is the same thing as 1 liter. Okay, so in 1 liter of solution, it means we'll be having 0.20 moles of these hydrogen ions. And that gives us 0.20 mole per dm cubed solution. And that will be the same number of moles for the anion side. But we don't need this. What we need is the hydrogen ion concentration. And that we already have from this expression. So that gives us an idea that the hydrogen ion concentration, that is this expression, is equal to 0.20 molar, that is mole per dm cubed. If you put this value, that's 0.20, into this equation, that's pH equals to minus log to base 10 of hydrogen ion concentration, and you press your calculator very properly, you will get this answer. That is 0.70. And that will be your pH. What does this value suggest? This suggests to you that this is a very concentrated acid, and this is a very strong acid, and it's also very concentrated. Okay. Let's check another example. This is another example. I intentionally put this example there using roughly the same parameters. In example 1, we have pH of 0.20 molar HNO3. In example 2, we have pH of a 0.20 molar H2SO4. This is no longer a monobasic acid. This is now a diprotic. Maybe you don't call it a diprotic acid, or maybe a dibasic acid. Okay. And what does this mean? It means that H2SO4 in solution will give us 2 moles of hydrogen ions and 1 mole of SO4 minus. It means to every 1 mole of H2SO4, there will be 2 moles of hydrogen ions that will be released in the solution. This implies that if you have 0.20 mole per dm cube of this acid in solution, every 0.2 mole in 1 dm cube of solution will be giving you 2 of that of the hydrogen ion concentration. Okay, so your hydrogen ion concentration will be 2 times 0.20, and that will be 0.40 mole per dm cubed. If you put this value into this equation for pH, that's pH equals to minus log to base 10 of hydrogen ion, then you have 0.40. This looks very tricky because when you have minus log to base 10 of 0.40, you're still having 0.40 back. It's not always like this, so you have to press your calculator very, very well. So press your calculator very, very properly so that you will get the accurate result. This is not just 0.40, it's approximated, maybe 0.39, maybe 7 or something. So it's approximated to 0.40. I hope you get this very well. Okay, so let's move on. So we have considered the pH of an aqueous solution of a strong acid. Now we want to consider the pH of an aqueous solution of a weak acid. Do we still use the same expression that we use for the strong acid for the weak acid? No. And this is the reason. We have to introduce the degree of dissociation of a weak acid into the expression that we'll use to calculate the pH of an aqueous solution of a weak acid. A weak acid does not dissociate completely in solution. So the degree of dissociation is less than 1. And we will need to introduce into this expression properly the activity of the solution. You may check textbooks. We put some references there for you online if you like to read more on how to derive expression for the pH of an aqueous solution of a weak acid. But because of our time, I've already written the expression for you. The pH of a weak acid solution can be given by pH equals to half pKa minus half log C. Half pKa minus half log C. Just remember this. This C is the concentration of the acid you are dealing with. And that is the concentration of the weak acid you are working with. This C is not the same thing as the hydrogen ion concentration. This C, let me say it again, it's not the same thing as the hydrogen ion concentration. It is the concentration of your acid. That's your weak acid. This Ka is the acid dissociation constant. And we have already said that we can relate it to pKa, just like you can relate the concentration of the hydrogen ion to pH. You can also relate the Ka to pKa. Okay, so note this equation 11 very, very well. And note that your pKa can be calculated using this expression, minus log to base 10 of Ka. Minus log to base 10 of Ka. So if you are given Ka, just get the negative logarithm of it to base 10 to be able to get your pKa, and put the value here, then divide it by 2, and also solve for the other part of the equation. And then you'll be able to get the pH of an aqueous solution of a weak acid. Let's look at an example under that. So under here, you are asked to calculate the pH of a 0.001 molar solution of methanoic acid. You are given the Ka of this acid. When you've been provided with this, the first thing you do is you know the correct equation you want to use, and that is equation 11. That is the equation for calculating the pH of an aqueous solution of a weak acid. If you like, you may first determine your pKa separately. If that it's convenient by you, you may first do that, and that is minus log to base 10 of 1.8 times 10 raised to power minus 4. We are only putting the value for Ka into that expression. And if you do that properly, you will get something like maybe 3.74. Something like 3.74. And if you divide it by 2, then you have 1.87. 1.87. Okay, but if you don't want to do it like that, you can just put the value for your Ka into the expression. You can put the value for the concentration of that your weak acid into this expression. Remember that we have said that how will you be able to know if something is a weak acid? Methanoic acid is an organic acid. And in the previous class, I already said that organic acids are weak acids. So anytime you are given organic acid, maybe lactic acid, citric acid, ethanoic acid, ascorbic acid, just think about the ethanoic acid, all of them, they are weak acids. They are weak acids. And the equation you use to calculate their pH is this equation 11. All right. So let's consider this very well. So you put the concentration, this 0.001. If you convert this one to indices form, you have 10 raised to power minus 3. You know how to do that. Just start shifting decimal points and all those things you did in primary school, maybe secondary school. Then you have 10 raised to power minus 3. And that's all we have put into this equation 11. If you press your calculator very well, you will get pH equals 3.37. However, you will see that I highlighted some letters in red, log. It's very easy to forget that there is a logarithm here and just write minus half into 1.8 times 10 raised to the power minus. If you do that, you will get your answer. You will get an answer. That may not be the correct answer, but definitely under the options you have, under the multiple choice, you will definitely see something that looks like what you have done. If you put log here at this end, but you forgot to put log at this other end also, you will get your answer there. If you do this one properly, but you forgot to put log here, you'll get your answer. And if you forget to put this half there in the expression and just use maybe 3.74, you will get your answer there. So it's okay. It will be advisable if you go through this calculation yourself. You pick your pen, you pick your book and calculate it on your own. Ensure that you don't borrow a calculator. The calculator you want to use should be your own calculator. So press it properly. If you're not familiar with how to use the calculator, you can just ask your friends or ask a neighbor, someone around who is familiar with how to use the calculator so that you're able to get the correct answer. All right. So that is how you get 3.37 as the pH of the solution. Let's move on. The pH of an aqueous solution of a strong base. We have already said that a strong base dissociates completely in solution, and according to Arrhenius' definition, it gives hydrogen ions in solution. So a strong base produces a weak conjugate acid if you're considering it from the view of Bronsted and Lowry. So let us move on. How can we calculate the pH of an aqueous solution of a strong base? You can still use the expression for calculating the pH of a strong acid, which is pH equals to minus log to base 10 of the concentration of the hydrogen ions. But for a base, where are you going to get the hydrogen ions? You may not be able to get the hydrogen ions. So what do you do about this hydrogen ion concentration? Instead of this hydrogen ion concentration, you can as well determine the hydrogen ion concentration from the hydroxide ion concentration. And how are they related? Remember one of the expressions that we wrote for you, something like pKw, which is equal to concentration of your hydrogen ions multiplied by the concentration of your hydroxide ions, and everything is equal to 14. How is it 14? You can do the mathematics yourself. Concentration of the hydrogen ions for water is 10 raised to power minus 7. For hydroxide ion also is 10 raised to power minus 7. If you put the two together, you have 10 raised to power minus 14. 10 raised to power minus 14. And if you get the negative logarithm of 10 raised to power minus 14, what would that give you? Just do your mathematics. Remember those things you did in secondary school. So you have minus into minus 14. Log to base 10 of 10 is 1. And minus times minus gives you plus. And that is how you have 14. Okay? That is if that's how you want to calculate it. But if you don't want to do that, you can use this expression I've written for you here. The concentration of the hydrogen ion equals to 10 raised to power minus 14. You now know where we got this 10 raised to power minus 14 from. Divided by concentration of the hydrogen ions. How will you determine the concentration of the hydrogen ions? It's not always the concentration of the solution. Remember what we did when we're calculating for an acid, a strong acid precisely. The concentration of the hydrogen ion can be related to how many number of moles of the hydrogen ions do you have when the acid dissociates. In this case also, how many number of moles of the hydroxide ions will you have when the base completely dissociates? I hope you get what I've just said. How many number of moles of the hydroxide ion will dissociate when that base goes into solution? For the case of sodium hydroxide, the number of moles for the OH is 1. If you have maybe CaOH2, then you may be thinking of how many number of moles of OH will you see there? Maybe 2. And so on and so forth. So, you know what we did? This is the concentration of the base. This is the same thing as the concentration of the sodium ions, because you relate them by ratio 1 to 1 to 1. And you also have the same for OH minus, which means that the hydroxide ion concentration that you have is 0.05 molar. Put 0.05 molar into this expression that you have, this one. Then you have 10 raised to the power minus 14 divided by 0.05. Just to remember that this 0.05 is the same thing as 5 times 10 raised to the power minus 2. So instead of writing 0.05, you can as well put there 5 times 10 raised to power minus 2. Okay? 5 times 10 raised to power minus 2. Okay, I think something is wrong with the expression, but we'll get over it. All right, so if you solve this properly, you have 10 raised to power minus 14 plus 2. That is as a numerator, because if you take this one up, that's what you will have, over 5. That's more or less like saying, okay, let me clear this one for you. That's more or less like say 1 over 5 times 10 raised to power minus 12. So this is not 5. This is 1 over 5 times 10 raised to power minus 12. I hope you're following. Okay? And if you put that, if you substitute this one properly into your equation, you will have a correct answer. It may not be this answer. So solve it from your own hand and you can put it in the chat section. I want to see the answer you have. All right? Okay. Let us look at this one. This pH of an aqueous solution of a base. pH of an aqueous solution of a base. Very briefly, let's just consider this. Okay? If you have a weak base, just remember the way we treated the weak acid. For the weak acid, we said that the pH is half pKa minus half log C. But for the base, you will have to introduce into the expression some OH. And how do you do that? Then you have to also consider what we call the ionic products. And you get the negative logarithm of that, of the ionic product. When you do this substitution very properly, we are not going to do it in this class, but you can also try it from your own hand, or maybe you study some textbooks. You will have this expression, which is pH equals to pKw minus pKb plus half log C. What is C? C is the molar concentration of your weak base. It's the molar concentration of your weak base. Okay? What is pKw? pKw is actually 14. Just take it this way. And how did we arrive at that? We have already said that this is the negative logarithm to base 10. What is your kW? That is 10 raised to power minus 14. And that was how we got 14 for the pKw. What is your pKb? You can actually get that one from your kb, which is the negative logarithm to base 10 of your kb. Negative logarithm to base 10 of your kb. If you solve this expression very properly, then you'll be able to get your pKb out and put it into this expression. You'll be able to get your pH out of this expression. Okay, now let me give you something to quickly do from your own hand. Now, let's say that you already know this pKw. That one is 14. You already have it. Let's say that your Kb is 10 raised to power minus 7. 10 raised to power minus 7. And maybe you are dealing with a weak base. You're considering a weak base. At the concentration of that, your weak base is, let's just put this value 0.001 molar. 0.001 molar. Okay? How are you going to solve this kind of equation? Your C is this, and that's your weak base. Let's assume that it can only release just one OH in solution. So what will you have from there? Your pH will be 14 minus half into the negative logarithm of your 10 raised to power minus 7. I think you're following that. Plus, okay, let's rub off part of this. All right. okay, plus half into log of the concentration, this C, and that is 0.001 molar. That is the same thing as saying 10 raised to power minus 3. If you do this very, very well, you will observe that this your minus 3 can actually come down here. According to the laws of logarithm that you are familiar with, or maybe if you're not familiar with, you can just go over it again. So you can have this minus log 3. It can come down here and you have minus 3 over 2 at this end. Then you can solve this log into 10 raised to power minus 7. This minus 7 can come here, so you have minus times minus becomes positive. So you have 7 over 2. So you have something like 14 plus 7 over 2 minus, then you start calculating what you have there. And that one can give you an idea of what your pH will be. Remember, this is just a hypothetical case. All right, let me give you this as a quiz to solve. Okay, and that will be under strong acid. I'm giving you this under strong acid to solve. So just look at this expression very well. For H2SO4, let's modify some values there in the comment section. Let's modify some values there. So where you have this 0.02, can you put 0.5 into this expression? 0.5 molar into this expression. What are you likely going to have? Let me see what you're typing in your comment section. What are you likely going to have if you put 0.5 molar into what we have here? What will this hydrogen ion concentration be? Okay. All right. I'm seeing some values there. I'm seeing 0, I'm seeing 1. I'm seeing 0 there, I'm seeing 1. Okay, 0, 1, 0, 1. Okay. All right, keep typing. It's okay. All right. Okay, let's go back to that slide. Okay, so for this, some of you got pH equals to 0. Some of you got pH equals to 1. Okay, keep typing. Let's see. We'll just take a poll of that. Those of you who got pH equals to 0, how did you arrive at that? Those of you who got pH equals to 1, how did you arrive at that? So let's say that maybe you just put 0.5 directly into this expression. That would have been a very wrong thing to do, because this acid H2SO4, each mole of H2SO4 will release 2 moles of hydrogen ion into the solution. And the concentration of the hydrogen ion in that case will be 2 times 0.5, and that is 1.0 molar as the concentration of the hydrogen ion. How many of you got that one correctly? How many of you got that one correctly? Okay. All right, all right, all right. Okay, I can see your responses. Okay, now let us take this one also. So you have that. Now we put this 1.0 into the equation for the pH. What are we going to have? Minus log into 1.0. And that's just more or less like saying to base 10. That's just more or less like saying minus log into base 10 of 1. What is log 1? Just press your calculator. Or maybe if you are you are familiar with logarithm scale. What is log 1? Log 1 is 0. 1 can be rewritten as 10 raised to the power 0, right? 10 raised to the power 0 is the same thing as 1. So instead of saying minus log 1, you could have as well said 10 raised to the power 0. So if you multiply, if you take the 0 here, so you have minus 0. Minus 0 is still 0. 0 times log 10 to base 10. Let me clear this. 0 times log 10 to base 10. Log 10 to base 10 is 1. Even if it is not 1, 0 times anything will automatically become 0. So your pH in this case is 0. All right. So most of you got it accurately. Most of you got it accurately. All right. So just trying to see how familiar you are with this concept. Let me take one question before we round off this class. Let me take one question just before we end this class. All right. If you want to ask a question, just raise your hand. Let me lower all your hands first. Okay. If you want to ask a question, let me see your hand. Taiwo Adeniyi. Taiwo Adeniyi, I'll be unmuting you now so you can ask your question.
Good morning, sir.
Yeah, good morning, Taiwo Adeniyi. What's your question?
From the expression of the pH of a big day, you said the dissociation constant or the degree of dissociation must be less than 5 degrees.
Okay, talk slowly. I cannot hear you.
Okay, I said in getting the pH of a weak acid, they say the degree of dissociation must be 5%. What is now 7% and above? Which equation are we going to use?
What if what?
If the degree of dissociation is now, if the percentage of the dissociation is now 7%, which equation are we going to use?
I can't actually hear you very properly. Maybe, I don't know the means you are using to talk. I can't really get what you are saying properly. Can you hear me?
I can hear you, sir.
Okay, but I cannot hear you properly. Okay, so state your question again.
Okay, I said the percentage of dissociation for a weak acid must be 5% or below 5%. Now, if it is now 7% or 45% and above, which equation are we going to use to get the pH?
All right. Okay. I think I've got your question now. So if the degree of dissociation, if it is maybe 7%, 5%, 45%, which equation are we going to use? Right?
Yes, sir.
Okay.
Yes, sir.
All right. You can lower your hands. We'll attend to that now. Okay. All right. Then you can also mute yourself. Okay. All right. So Taiwo has asked a very good question. Let's go back to the slide and look at it. His question is this. If the degree of dissociation is definitely, if it's not 1, that is if it's not 100%, which equation are we going to use? Maybe it is 5% or it is 7%, or maybe it is, which other one is that? Possibly it is 5% or 7% or 45%. How are you going to describe which equation are we going to use? Just let us take some slides back. We have already said that for the degree of dissociation, you use, okay, degree of dissociation can be related to activity. And the activity is the degree of dissociation multiplied by, let's say, the concentration. And that is the concentration you have of that your maybe weak acid or a weak base. You talk about degree of dissociation less than 1 when you are talking about either a weak acid or a weak base. That is when you have a weak electrolyte. That's when we make reference to degree of dissociation. And if you have that, remember that normally we should be using activity for weak acid and for weak bases. And in order to simplify the expressions we have, that was why we introduced other concepts like concentration and the molar concentration of the hydrogen ions. So look at expressions like what we have here. There are some, let me put it this way, there are some approximations we have put into this expression, and that is we have assumed that this degree of dissociation is very low for a weak electrolyte and it is far less than 1. So this 1 minus alpha has automatically turned to 1. You can calculate, maybe depending on what you're provided with, just look at this expression. You can determine your K out of the expression. If you are given a degree of dissociation of 0.7, that's like saying 70%, and you know the concentration of the weak electrolyte, maybe it is 5, maybe it's 5 molar, or maybe it's 0.5 molar, depending on what you're provided with. You just calculate your K from this expression. Just multiply the square of your degree of dissociation. Let me clear it. You multiply the square of your degree of dissociation by the concentration you are provided with. If it is 0.5, fine. If it is anything you are provided, just multiply it by it. You will get your K out. If you're able to get your K for an acid, that will be Ka. For base, that will be Kb, depending on what you are dealing with. Then you can start looking for the expression that relates the pH of the weak electrolyte, or maybe the pH of a weak acid, to the Ka, and also the log of the concentration that you are working with. So you can now use this expression, pH equals to half of pKa, noting that you have already calculated your Ka from this equation 2. Sorry, I'm coming. Okay, then minus half of log to base C. So you can use this expression to calculate the pH of a weak electrolyte when you are given the degree of dissociation, and you will have calculated your K from this equation 2. I think I've been able to attend to your question. Our time is fast spent. If you have other questions for us, you can put it under the chat section, or you can send your question to the designated email of this course, che156@stu.ui.edu.ng. Someone is asking what's the difference between pH and pKa. Okay? pKa, it relates directly to the acid dissociation constant, and we use it basically for a weak electrolyte, let's say a weak acid. pH relates to the concentration of the hydrogen ions. How well does the hydrogen ion dissociate? Then you think about the Ka or the pKa. An acid that dissociates properly, that dissociates very well with high Ka value, will definitely tend towards a strong acid. But if you are now talking about the concentration of the hydrogen ion you talk about the pH. That's how we call it the potence hydrogen. That's the power to which on the logarithmic scale, that's the power of that hydrogen ion concentration to base 10. All right. We'll need to stop the class here. Thank you. We'll be meeting again tomorrow by God's grace between 5 and 6. Let me wish you a very great day.